In this video, we will review sequences from pre-calculus as well as introduce some terminology that you'll need for sequences and our first unit on geometric series and binomial theorem. The reason we're starting this course with sequences and series and so forth is that all of what we're going to be studying in Calculus 2, which is what is going to be tested on the latter part of the IB Math HL exam, as well as the new material that will be on the AP Calculus BC exam, is all based on the study of infinite processes, infinite sequences of numbers, and more so infinitely adding together the sequences or infinite series. So we're going to lay a foundation here and study this throughout the course. Some terms we should know. Just a basic number sequence is just an ordered list of numbers defined by a rule. An ordered list of numbers defined by a rule. That rule might have a formal equation. This rule might be just a description of how to calculate new values in the rule, like in words, but there is some rule that exists. We're going to mostly focus on sequences in this course that have an equation that defines each term, but that's not to say that sequences in general won't. And many of you will at some point take courses that will look further into more general sequences. The terms or the members of a sequence is just an individual number in them. Number in the sequence. The symbols we use for those, in general, we use for a sequence. We give the sequence a name, usually a single letter like A, or sometimes IB likes to use U for the sequence. And then the subscript, usually with either an I or an N, is called an index. And this index tells you where you're at. This is the, not T, but I, the ith member of the sequence. So for example, like A1 is the first member. Sequences can be either finite or infinite. Finite sequences are, well, they're finite, they terminate or they end. These are fine, but they're kind of boring because they always behave the same way. Namely, they stop, and if you add all the terms together, you can easily calculate what that is. Whereas infinite sequences tend to be more interesting in that they go on forever. And we're going to see that the sums of these infinite sequences can be intriguing. Sometimes they blow up to infinity, but there are definite cases when they don't. And those are the things we're going to be studying throughout the course. Before we get there, though, we should be able to describe what some sequences are. We should be able, both in pictures, words, in formulas, and so on and so forth. So let's take a look at a couple examples here. Let's see. What are some of the patterns we see in here? And then we're going to write down the next three terms. The pattern for this first one jumps at me right away. It's just subtracting 4 each time. So I think in words, we're just subtracting 4. And the next three terms should be 79, 75, and 71. This sequence doesn't jump out at me as quickly, but I can figure it out. I recognize these numbers as these are some perfect squares. Although what's being squared doesn't really make a ton of sense to me. Like 1 squared is 1, 4 squared is 16, 9 squared is 81, 16 squared. Like I mean, this is like, well, the square of perfect squares. But Oh, but maybe that's a little more explicitly. Square something is to the fourth power. This to me, I think 1 to the fourth power is 1, 2 to the fourth power is 16, 3 to the fourth power is 81, 4 to the fourth power is 256. So I think the next three terms should be 5 to the fourth power, 6 to the fourth power, and 7 to the fourth power. If you're not sure what, if you want to, you can use a calculator to figure out what these values are. On the AP exam and the IB exam, if a question like this was asked, you could definitely just leave it as in exponent form. But if you really want to know what these values are, just take your calculator. We can use exponent function to get the 625, 1,296, and 2,401. This third sequence, the pattern doesn't jump out to me right away. Add 1, then 2, then add 2 again, then add 4. Like, it's not consistently adding the same thing. We're definitely not multiplying the same thing every time through. It's not like exponents like up here. These are all whole numbers, so there's not like square roots or fractions really involved. Although this sequence of numbers is very famous, and you should recognize what this sequence is. If you can come up with a formula that calculates every value in this, you're going to be a very famous person, because currently there's not one known, and it's an outstanding open problem in math. If you could calculate one, you'd be very likely one of the most famous mathematicians alive, if you could do that. And if you do, I would really enjoy getting cited as an inspiration for your mathematical career. However, we can write down what these numbers are. These numbers are a famous sequence of numbers. These are the prime numbers. And the next three prime numbers after 11 are 13, then 17, then 19. Lastly, this fourth sequence, this is regular, has a pretty regular pattern. It starts at 9, then goes down 1 to 8, and then up 2 to 10, then down 3 to 7, then up 4 to 11. It looks like I'm taking the previous number and adding something consistently. Recursively, or I'm using the previous number. I think I'm, like in words, here it looks like I'm taking the previous number and then adding the next bigger number after that. So like, how might I write that? Like, if you remember recursive sequences from pre-calculus, I'll get the next value by taking the value I'm at and then adding something to it, it looks like. So for instance, maybe we take a few examples in here. If this is k, if this is the first one, then 8 is 2, 10 is 3, 7 is 4, 11 is 5. So to get to 8, that would be 1 plus 1 is 2. I'm going to take k1 and add -1 to it. When I want to get to k equals 3, I want to take k equals the second spot and add 2 to it. So it looks like one way to write this would be to get to the k plus 1 index is to take whatever values at the previous index and add the previous index to it. But I'm not always adding the index. Sometimes I'm subtracting, sometimes I'm adding. It looks like I'm adding either positive or negative value of this k, which means I want the sign to alternate. And a really classic and important way to do that is to represent by multiplying this value by a power of -1. Because -1 is either +1 or -1, depending on what exponent you use. If the exponent is odd, then the -1 to an odd power is -1, -1 to an even power is +1. So we can alternate the sign by just putting either positive or negative power up here. I think when k itself is odd, we want to add the negative value. But when k itself is even, we're going to add positive. So when k is odd, we want odd exponents. Maybe the exponent should match the value of k. So I think this could be like a recursive. This would be a recursive rule for this sequence. So knowing that, what should the next few terms be? Looks like I added 4 to get to 11, so I should subtract 5 to get to the next value. That's 6. I should take 6 and add 6 to it, and add the next value up. That's 12. Then I should take 12 and subtract 7, and that gets me to 5. Should be able to illustrate sequences in other ways. Here's a list of various things you can do to describe a sequence. And again, some are profound, some really aren't. It's just a review of things that you've hopefully seen in the past. Maybe the easiest way to list a sequence is to just list all the terms. If a sequence is built by like building a pyramid, starting at this top row and then going down, and each value is the number of bricks in this sequence, then I think the terms of the sequence is pretty clearly 3, then 4, then 5, then 6, then 7, and so on and so forth. How would you describe this sequence? I think this sequence starts at 3, start at 3, and then add 1 each time. To get to the next term. I think an explicit formula for this would be start at 3, and then I'm going to add, looks like whatever row I'm at, minus 1. If I'm at the second row, I want to add 1, so 2 minus 1 is 1. If I'm at the third row, I want to add 2 more bricks to 3 to get to 5. So I think I want to take whatever row I'm at, take away 1. And you can kind of clearly see that if you're in the first row, you want to start at 3 and add nothing to it. 1 minus 1 would be 0. I think a recurrence or a recursive formula for this would be, we write, if you recall from previous courses, to write a recursive formula, you need a starting point. So A1 is 3. And then we need a rule for how to get to the next one. N plus 1 is take where you're at and add 1. And you could, lastly, you could represent this kind of as a graph. You could graph the terms of the sequence where you're at. And then you could graph the outputs. And it looks like we start at 3, and then 4, and then 5, and then 6, and so on.